Hey there, astronomy students. This is part B of podcast 8.1 since I needed to add some more information. It cut me off. Okay, so we were talking about the solar cycle, and we said after 11 years, the north and south is going to actually be reversed. So what happens is the sunspots are typically going to start out roughly around the equator, and then they're going to move laterally north and south. After 11 years, it reverses, so it actually goes backwards, and you'll notice that here there's a 22-year period. There's an 11-year cycle here, and then another 11-year cycle here, which is actually kind of a reverse, which gives you a total of a 22-year cycle for the entire solar cycle. I know, crazy, right? All right, so the Maunder minimum sunspot number fluctuates over a longer time scale. So the Maunder minimum is this period in time here. Let me get my pen back. It's this period in time here where you'll notice that the sunspots were at a complete and total minimum, right? And this is during what they called the Little Ice Age, when the record temperatures of the Earth were a lot colder than they normally would be. Okay. So this shows that on average, the number of sunspots here was really, really small, and then look, they peaked back up. Well, this is all pretty normal, Looks like it's getting a little bit higher here, but it's not too bad. So there is a chance we could go back. There's a chance that we could stay. We'll see. All right. Yeah, there you go. All right, sun's magnetic dynamo. Let's see. Sun rotates faster at the equator than near the poles. I've already said that. So when that happens, it causes a dynamic rotation, right? Or differential rotation, excuse me, and that could be what's responsible for the magnetic activity of the sun. That's what they believe is responsible for the magnetic activity of the sun, right? Because this is rotating much faster than these up here at the top would be. After 11 years, the magnetic field pattern becomes so complex that the field structure is rearranged, which is what I was talking about earlier, and a new magnetic field structure, which is similar to the original one, but it's actually reversed. And that's why, let's go back here real quick. That's why here we see that it's a total of 22 years because it goes through the first 11 years, but then it's going through the second 11 years, which is actually a reversal of the first. Okay? So it's a total of 22 years. All right, so here it just says, for simplicity, a single line on the solar magnetic field is shown. Differential rotation drags the equatorial part of the magnetic field ahead. As the sun rotates, the magnetic field is eventually dragged all the way around because remember the middle is rotating faster than the top and the bottom. And it keeps going faster and faster, so this differential rotation wraps the sun in many turns of its magnetic field. It kind of twists it up. And then these twists, these loops of tangled magnetic field rise through the surface, and that's where you get your sunspots, and that's how they occur. Okay, so new 11-year cycle starts with reverse magnetic field orientation. Okay, prominence. So prominences, here we go. Prominences are going to be, I'm trying to figure out what the word is I put on your ionized gases trapped in magnetic arches. That's it. Ionized gases which are trapped in magnetic arches. Some of them are eruptive and they escape the magnetic field and result in solar flares, which we'll see in just a little bit. But here's a prominence. It's relatively cool gas. It's anywhere between 60 and 80,000 Kelvin. I know, relatively cool, right? Okay, but you got to think that these are coming out in an area where majority of the stuff is, anywhere to 1,000,000 Kelvin, right? So you've got these gases that are looping out of the sun's photosphere and falling along these magnetic loops. Well, sometimes, here it says, may be seen as dark filaments against a bright background of the photosphere. And sometimes these photospheres don't actually loop, or prominences don't actually loop back around. And that's what we would end up calling solar flares. And these can cause, extreme solar flares can disrupt They can cause surges in electrical lines, which happened back in the 90s, I believe. Late 90s, early 2000s, there was a big solar flare that messed up a lot of stuff along the East Coast. Damage to the Earth's satellites. It can disrupt navigation systems, and it can actually distort the Earth's magnetic field. And it's also what causes the aurora borealis, which is the northern lights. Right. Oh, and these are just some ultraviolet images of this, so you can see up here, this would be the size of the Earth, teeny, teeny, tiny. And here is a solar flare coming off. The solar flare is huge in comparison to the Earth. Right. Okay, so space weather. Space weather, these would be the aurora borealis or aurora, the northern lights, and it's from the upper atmosphere gases. Excuse me. Then we have our coronal mass ejections, which are going to be violent gusts in the solar winds that help to create the auroras. Coronal holes, which are places where the I just lost my train of thought. I'm so sorry. It's where the flare or the I guess I'd say solar flare doesn't loop back and produces holes, coronal holes. I know I had the word here, but I can't think of what it is right now, so I am so sorry. But X-ray images of this shows that there are holes in these corona. It's where the prominences will gust out, so the solar flares gust out, and they don't loop back in, and so it produces these coronal holes, or these holes in the corona. Right? And that's the corona hole is what they say produces the solar winds. So that's where those winds come from, the solar winds come from. All right, so solar constant. The energy received from the sun is essential for all life on Earth. So if we wanted to know the amount of energy received from the sun in all wavelengths and all radiation, we say we can use the solar constant to help express that. And so the solar constant is 1,360 joules per meter squared per second. Okay. So what does that mean? Well, this is the energy that's received in the form of all radiation per unit time per unit surface area. Okay, so the solar constant, if we were to, I think that's it, so if we were to change the solar constant by 1%, we would change the Earth's average atmosphere by 1 to 2 degrees Celsius. Okay, so you think, well, whoop-de-doo, Mr. York, what's the big deal about changing the atmosphere 1 to 2 degrees Celsius? Well, during the last ice age, the average temperature was about 5 degrees Celsius lower than it is right now. So think 1 to 2 degrees Celsius, that'd be pretty cold or pretty hot, right? Okay, so that concludes the sun, and I guess I'll see you in class.